In this section, we'll study computational algorithms for finding eigenvalues and eigenvectors. The power method is an iterative algorithm. Once a square metric is given, then the algorithm tries to find the largest eigenvalue of the metric and its corresponding eigenvector. To apply the power method, we need to assume that A, the metric has n linearly independent eigenvectors and exactly one eigenvalue that is largest in magnitude. Let's say lambda 1, then lambda 1 is strictly larger than lambda 2 in modulus, and the others doesn't require the strict inequality. So one eigenvalue is strictly larger than others in magnitude, then we can apply the power method. Okay. Now, because we assumed that the eigenvectors are linear independent, they form a basis so that for any vector in Rn, we can express it as a linear combination of eigenvectors. So along with some coefficients, beta j. Now, for this expression, we multiply A. Then, for this finite summation, A can be applied here for each eigenvector. But A Vj is same as lambda j Vj. So we have this term. Once we multiply one more time A, then we can get here lambda j squared. In general, after k times of multiplication, we have here lambda j k. Now we manipulate the equation here in this way. Now we try to factor out lambda 1 to the k from there on. Then we have here lambda 1 to the k in the denominator. So this is explicit detailed equation. Now we put here lambda 1 over lambda 1, which is 1. So that is basically beta 1 V1. And now we have these terms. However, we assumed in the beginning lambda 1 is strictly larger than the other eigenvalues. So that here this value will approach 0 as k increases. So when k becomes larger and larger, then a to the kx in limit will be the same as here limit and lambda 1 to the k, and this term is always beta 1 v1. So we reach this equation. Now if you look at this one, then the equation itself is almost useless. The reason is, once lambda 1 is larger than 1 in modulus, then this value will blow up. And if lambda 1 is less than 1 in modulus, then it will approach to 0 vector. So in either case, it is very hard to decide the largest eigenvalue, lambda 1, and its corresponding eigenvector, v1. To take care of that possibility, we may try to apply some scaling. So in each multiplication of A, we try to scale out. Then we can see that, for example, in this case, after one more application of A, we have that one as lambda 1 times expanded or shrinked. If lambda 1 is larger than 1, then it is expanding. And if lambda 1 is smaller than 1, then it is shrinking. So try to measure. So in the beginning, for example, this portion has length 1, then we can find the scaling factor, which is the same as, almost the same as the largest eigenvalue. So scaling idea will give you really an answer to find the largest eigenvalue. Okay, let's see this algorithm, pseudocode for the power iteration. We start with any initial non-zero vector, and we can make x0 is normalized by its length, so that eventually in x0, the largest value in modulus will be 1. It's normalized. And for each xk, now we multiply a, and we save it here, and measure the size, and divide by the magnitude. So in this case, you may assume that one, mu k, is approaching to lambda 1. In fact, absolute value of lambda 1. And also, later on, this portion, x is approaching to the corresponding eigenvector v1. Here we have a claim xk, mu k are a sequence produced by the power method here. Then xk is converting to v1, and mu k is converting to absolute value of lambda 1. More precisely, the power method converges as here. The mu k is converting to here absolute value of lambda 1 with this error. So that as k increases, the lambda 2 over lambda 1 becomes smaller and smaller, so that this term will approach 0. So eventually, as k increases, mu k will convert to lambda 1 absolute value. Now look at here. Now among these terms, and now this one is approaching 0. However, in a sense, the slowest, because later on the lambda values are smaller than lambda 2 in modulus. So this one is smaller in modulus, so that these remaining terms will go to 0 more rapidly, so that the dominant error will be this term. That's the reason we are using this term as the dominant error. So let's see the computation results. A is given in this way, and it has eigenvalues and eigenvectors as follows. If you're using EIG built-in function in MathTalent, then you can find these eigenvalues and corresponding eigenvectors. Minus x, minus 3, minus 1 are eigenvalues, and their corresponding eigenvectors are here, these 3 columns. And this one is for minus x, the middle column is for minus 3, and the last column is for minus 1. Now, we'll try to find this eigenvalue and eigenvector by using the power method. Here we defined the metric A, and this is a format for print here. Now we start with x0, 1, 0, 0. This is indicating transport, so we consider one vector, the vertical vector 1, 0, 0. Now A is multiplied to become y for that one. Now rather than taking here maximum norm we try to find the position where the maximum value occurs in modulus. Take here absolute value and try to find the maximum, and that is position of the maximum in this array. After finding the position, we try to read the value to be mu, so that that is now in fact, this value is the same as the maximum norm along with the corresponding sign, so that that will be plus minus here y, the maximum norm. So once the corresponding position value is negative, then it will be negative. And if it is positive, then you will have a positive, because we are getting the value practically from the position. Okay. After getting mu, we just scale the vector y. Then we assign, we get new x. And each iteration, we try to print out from 1 to 10. So let's see what happened. And last one is the difference between mu and minus x. Minus x is the largest eigenvalue. Let's see the error. Okay, after one iteration, we have this vector. We start from 1, 0, 0, and we have that one. And at the moment, the mu is minus 4. And second iteration, third iteration, and after 10 iteration, you can see here now the vector x is 1, that is almost minus 1, and this is almost 1. Here, for this eigenvalue, the eigenvector is 1, minus 1, and 1. After 10 iteration, we have near around a vector near around v1. So if you do more iterations, then you can get better approximation. Now also the mu is approaching to minus x apparently, and here this is error between minus x. Here the error is 0.011. Now that is about twice of that, and again twice. That means in each iteration, error is reduced by a factor of 2. That is coming from here. Okay, that is, then earlier we said that the error is converging as order of this one, lambda 2 over lambda 1. For this problem, and this is lambda 1, there's lambda 2, so that the ratio is half. So that is half. So that's the reason here error is reduced by a factor of 2. Okay. Now we'll consider the inverse power method. Inverse power method is used for finding an eigenvalue near around some prescribed value q. It's a variant of the power method, and we can find some specific eigenvalue near around some value q. To formulate the inverse power method, we start from that equation. A vi is lambda I vi. That means that lambda I vi are eigenpairs of the metric A. Now we subtract q along the diagonal, then we can get that one. This means that for this metric, the corresponding eigenvalues are this one, and the associated eigenvectors are the same as original one, the vi. Now, we when here Q is none of these lambda 1 to lambda n, then this is invertible. So we apply inverse of this metric and divide by this quantity to get that equation. And that means that here for this metric, and this quantity is an eigenvalue and its corresponding eigenvector is Vi. So we can say here now eigenvalues of A minus Qi inverse are this one. Here, for example, now lambda 2 is nearest to Q, then because of this reciprocals, this value will be largest one, so that by using the power method for along with this metric, we can find this quantity and the corresponding eigenvector of V2. So that's the idea. Here we have algorithm. Now start with arbitrary non-zero vector, and we initialize it with length 1 and divide by its length so that x0 has the magnitude 1 in modulus. Now we multiply, in each iteration, multiply this metric to the previous vector, and we can get yk. And now we try to get measure the here maximum norm of yk, and here divide by mu k, so that we scale to get new vector. In this case, mu k will approach to one eigenvalue of that metric, right? So it's related with A minus Q and inverse, right? So that is one of these one, basically, so that here mu k is basically now one of these eigenvectors. So that let's say that is one of lambda minus q. Of course, lambda is eigenvalue of here A. Okay. Now, if we want to recover an eigenvalue of A, then we have to solve this equation for lambda. So we take reciprocal first, so that 1 over mu k equal now lambda minus q, and from here we can get lambda equal here 1 over mu k and plus q. So that is exactly this one. So lambda k is one eigen value. It is approached to an eigenvalue of A, and in fact nearest to Q. Okay, here now we consider the same metric as in the last example, and we choose Q as now minus 5 over 2. The eigenvalue for that one is minus x, minus 3, and minus 1. Here we choose Q as minus 5 over 2. So once we are using the inverse power method with this Q, then we'll find the eigenvalue minus 3. Okay. Let's see if it is really working that way. So same metric and the format for printing, and we choose Q and the same initial vector, and we try to form the inverse of A minus Qi, and in each iteration we multiply B to get Y, and the same way we try to get the position index from the absolute value of Y, and we take the value mu. So this mu k, mu is eigenvalue of b. That is related to b. Now then, after scaling, and we try to get lambda. Now that is eigenvalue of a. So it is approaching to an eigenvalue of a. So here in printout, the last one is error, the difference between -3 and lambda. Let's see how lambda is changing. Again, we run 10 times, and now start with 100. After 10 iteration, we have that vector. It must be an approach to eigenvector for the second one. Now here lambda is approaching to -3, the second eigenvalue, and the error is reducing in this way. Now because of roundup, it looks 8 times, but if you go over there, then it's about 7 times. That is 7 times reduced, and again 7 times reduced. Why we have this 7? That's the question here. Now for this metric, and eigenvalues are given here and here and here, and the initial vector can be written as a linear combination of v1 and v2, so that we may check the ratio by using these two eigenvalues. Now this is the largest one, and now this is, in fact, this is the second largest one, but there's no component for this one, so that the convergence will happen along with that ratio, which is 7. So we have here reduction of error by a factor of 7 in each iteration. Okay. Okay, that's the end of the section. Thank you.